I would like to welcome you to the 7th class in the FISH 501 Ecosystem Modeling course. Today, Carl Walters is going to give us an introduction about dynamic modeling, and he's going to take us through how to create a dynamic model in Excel. And it's going to be, please follow along on your own. And that's about it, what we're going to be doing for the next couple of hours. So let me start though by acknowledging that UBC is at Coast Salish territory, and that we are thus at the traditional unceded and ancestral lands of the Musqueam, Tsleil-Waututh and Squamish people, and that we also acknowledge that for this course here we have participation very widely, 29 countries, and we very much appreciate that and that interest it expresses, and we bid you welcome to follow this course, be it on Zoom or on Facebook Live or later on YouTube. The recordings are there. If you look at the Ecopath YouTube channel, you can find them, and also at the Ecopath Consortium Facebook page. The lectures are available at the course website, and you can see the link to the course website here. And finally, just as I did a couple of days ago, or rather last Thursday, I would like to welcome Carl Walters to give this presentation. And I will cut the introduction short, since I was more wordy a few days ago, and instead turn it over to Carl. Though one thing, there was a question coming after last week's class, and I think Santiago, would you like to introduce that question before we start off with dynamic modeling?
I have it right here. So the question was by Francesc Cordó, and it was: the Beverton Hold recruitment model predicts that once a certain juvenile fish density is available, the number of recruits surviving will not increase with an increase of spawning. Therefore, even though they tried to increase the coho by adding hatchery smolts, the whole spawner population did not increase, but kept without changing, and finally it even declined. My question then my question is regarding the one very scary prediction. If I understand correctly, Dr. Walters was here suggesting that this model would make recruitment particularly vulnerable to predation, and I don't understand why. If the recruitment is more or less independent of spawning, does this not leave a wider margin for predators to feed without really affecting the final recruitment?
Okay, that's a good question. Basically, what we think could be going on, or what we used to think was going on out there, was that when juvenile densities increased in the Georgia Strait, the juvenile foraging was concentrated in surface waters, the foraging arena structure, so that there was more intense intraspecific competition between the hatchery and wild fish. But in order to survive through their lives, these fish know in an evolutionary sense that they have to reach a certain size in order to get through the winter. Well, with more competitors and lower food densities, that means they have to spend more time foraging each day in order to achieve that base growth rate that in an evolutionary sense they know they have to achieve to make it through their lives. It's that increase in foraging time increases their exposure to predators, so that they become more sensitive to changes in predator abundance when there are more juveniles competing with each other. That's what increases the sensitivity of the mortality, of the predation mortality rate. That sensitivity is driven by intraspecific competition. Okay? Spell. Now, what I'm going to do is just go through a very brief PowerPoint presentation about what a dynamic model is and how we construct them, and point out that Excel that I'm going to be using to show you how to do dynamic modeling It remains one of the most powerful tools for dynamic modeling, and you should be learning the techniques and conventions that I'm going to show you today for Excel modeling. Most people don't realize that most of the really complicated models we use today, like Ecosim and a lot of complicated population models, they're constructed in programming languages like BASIC and R and Fortran and so on like that. But people who construct those models have learned that it's a really good idea to build the model first in Excel if it isn't too complex, and make sure, because it's much easier in Excel to make sure that you get the model structure right. Then you build the model in R or BASIC or so on, and you make damn sure that it matches what you've already figured out is the right way, the right predictions, at least what the equations predict in Excel. So it's very much worthwhile to actually learn for yourself these techniques. I'm going to show them to you rather quickly. You won't up all of the details. The way to learn to do this stuff is like other things, is to do it yourself. So you're not going to learn a lot from this talk unless you actually go and do the things that I'm about to show you.
Carl, I have to mention it here for historic interest. Ecosim was actually constructed that way first.
Yeah, I told them
in
last
Excel.
week. Ecosim
Okay.
was the first Ecosim was built in Excel. Our first villainized COVID models were built in Excel, and everybody's age structured models that they now use in R for stock assessments, they build them first in Excel. It goes on like that. It's a little secret that experienced modelers learn is don't trust programming languages because they make some of these calculations not transparent. Everything you do in Excel is completely transparent, as you will see. Okay, well, dynamic modeling is about prediction over time, and there are two basic approaches that human beings use to make predictions over time. One of them is basically to make observations over time and then to extrapolate those observations. Most human intuitive extrapolations are straight lines like this from pattern in the data. And you can really see that when you listen to news people who present pictures of the COVID dynamics, because what they'll do is they'll almost always take the recent COVID growth rate and they'll say it should be look like a straight line. And then they express great shock when you find out that the actual observations are curving upward in an exponential growth pattern. So trend prediction, simple trend prediction like this is not the intuition behind it is not a good way to look at dynamic systems over time. And people have known this for a long time. So what we've generally tried to do is to change over to this other basic way of thinking about prediction, which is to think about it as starting with the state of a system now, constructing rules for how the state should affect the change in the system, use those rules to predict a short time into the future to the next state of the system, then circle back or loop, as we say, to make that next state the state now, and then apply the same rules for change, but with a different value for the state, so that we predict cumulative change over time using a set of rules that we think are reasonable for any short period of time, but that may not apply cumulatively over longer periods of time. So every dynamic model that you'll see has this same structure. It has the current state, rules for how state affect change, short prediction, circle back and do that again. Okay, now when you look at these rules for change, the rules for change come in two flavors. The first flavor is what's called a tautology. A tautology is a statement like population next year equals population this year plus births minus deaths. Now, if we're talking about a population we know is closed to migration and doesn't have any spontaneous creation, then this statement about population change is a tautology. It's true by virtue of the way I defined the words population, births, and deaths. Fair enough. There's no way this statement can be, this tautology can be wrong. If you went out and measured a population this year and measured it next year and measured the births and measured the deaths, and they didn't add up, if the next population was not the population that you'd estimated the first time, plus births minus deaths, what would you say? You wouldn't say this rule is wrong. You'd say that you must have misestimated the population size, or births or deaths. Something had to be wrong in the way you define those things. Now, so a tautology is a statement that's true by virtue of the way you use the words in the sentence, and an equation is a sentence. Why do it? Why bother to express such truisms? Well, the reason for it is that what tautologies do is to break the problem of prediction into components. Prediction components, births and deaths in a simple population model, so that we can focus on how to predict those components rather than to predict population size directly with some single rule. So if we can get a good rule for predicting births, a rule for the birth part, and a rule for the death part, then we can then use the tautology to combine those rules to predict the next state. The other flavor in the rules are functional relationships. These are specific, theoretically testable propositions about how these components of change, births and deaths, vary over time with the state of the system and perhaps other external disturbances and so on. So a functional relationship is an empirical or theoretical prediction about components of change in tautologies. Everybody with me? So this is a simple bit of logic that's helpful in modeling, is to realize that you're going to be dealing with two kinds of things. Statements about how components of change interact or accumulate in their effects, and then specific predictions about those components. This also, thinking about it this way, allows you to recognize that these functional relationships can often be represented in a hierarchical way. So I can break down births into births by different ages and sexes of parents, and with different birth rates and so on like that. So I can progressively complicate the functional relationships in a hierarchical way to build more realistic models. Yet the same general tautology will allow me to combine those more complicated calculations back into an overall prediction. Just an aside here, there are models floating around today that are of this basic structure that are actually not correct because of errors in the statements about the components of change. And just because I say that you add births and subtract deaths, I'm not saying that deaths are independent of births. Death rate may very well depend on the birth rate, because some of the animals that die will be those that were born before the next time. Okay, now there's two basic ways to make predictions and change over time. I just showed you what's called a difference equation representation, where I say population next year is population this year plus births that I'm proposing in this example to be proportional to how many animals are there to give birth, and then minus a mortality or death rate that I'm proposing to just depend on how many animals are there. The other way of representing dynamics is by, in order to avoid problems like the fact that some of the deaths will actually be of the animals that were born during a discrete period of time, is instead to write an equation for how fast things are changing at any moment in time. That's the rate of change of numbers. and write it as a birth rate minus mortality rate. When you write a model tautology in this form, in the differential form, it's much more likely that the rate components will be independent of one another over at least a short period of time, so that you won't make the mistake of incorrectly predicting that none of the births die, none of the animals that were born died over the discrete time interval. The way we solve these differential equations, it's a long history in applied mathematics, is we predict the numbers after a short period of time, delta t, a time increment, as the numbers we start with plus the rate of change times time step. This is called the Euler method for stepping forward in time, applying rules for change over a short increment of time, delta t. It turns out for the models that we use in ecology, this thing called the Euler method doesn't work properly. It underpredicts change. So what we do instead of using the Euler step, which is to calculate how fast things are changing and then apply that rate for a short time step, we use more elaborate what are called numerical integration methods for solving differential equations. One of the most useful of those and simple of those integration methods that's really easy to implement in Excel is what's called the Adams-Basford or predictor-corrector method. And what we do with it is we calculate the derivative of the abundance, if you like, at how fast it's changing at time t. And then we also look back at how fast it was changing at an earlier time step. Okay, and then we predict forward in time, instead, again with the starting numbers, but we use this little bit more complicated formula, dt times 3x 3 times the derivative now minus the derivative times time before, and then there should be a bracket here. I'm sorry, that's an error. Divided by 2. So I'll show you how we do this. What happens when you use two of these derivatives is that you recognize that as you're predicting forward in time, the dynamics are curving. Exponential growth creates a curve in time. And using the derivative at 2 times lets you correct for the emerging curvature in the dynamics over time. Now I'm going to go over the spreadsheet thing, and I'll just point out here that this idea of applying rules for change in order to make predictions was built into the earliest spreadsheets back in around 1980 when notebook computers or personal computers first appeared. And people like Microsoft realized that they should set those spreadsheets up in a way that allowed easy modeling over time. Okay. Now, before we go to Excel, let me point out here that the rules for change, the functional relationships involved in the rules for change, include 2 types of numbers. So the numbers in the spreadsheet will be of 2 kinds. One of them are state variables that change over time, like number of animals in a population. And then there are other numbers that we treat as or pretend to be constant over time when we're making a prediction. Those are called parameters. Like if I assume that the per capita birth rate of a population doesn't change, that birth rate is then called a parameter. And one of the first things you have to learn in Excel is to keep these state variables and parameters separate from each other in the spreadsheet. Okay. So now what I'm going to do is see if I can move to the spreadsheet. To a simple Excel spreadsheet. Now I'm going to assume that everybody in this class has seen a spreadsheet, right? I mean, if you haven't seen a spreadsheet, spreadsheet like Excel, you certainly need to do so. Fair enough. And I'm going to blow this up to fill the whole screen. And I can't use the pretty laser pointer. I need to use the Excel pointer. Billy, is the Excel pointer visible on the screen? That
Yep, it's visible.
cross-shaped thing. Is it visible to everybody?
Yeah.
Okay, now just to make this a little easier to see, I'm gonna blow this up a little bit. Now the way I build models and that I recommend everybody else does is I use the first put parameters for models. Things that aren't going to change and put definitions for them. And then in later columns, I put the rules for change and how they change. And I always use the convention that rows represent times. So as I go down from one row to the next, I'm predicting from one time step to the next. Fair enough? Now, other people use other conventions. They predict time across the rows and things like that. Turns out the way I do it is much easier when you want to do things like draw graphs of your predictions over time. It's best to have the time go down the spreadsheet from row to row. Okay, so I'm going to build a simple population model, and I'm going to have two parameters, BR, the birth rate, and MR, the mortality rate. All right, and in column C here, I'm going to remind myself that this is the birth rate, per capita birth rate, and this is a per capita death rate. Now, what I'm going to do is show you is a very important trick in programming in general is to name the cells where the parameters are going to be. And the way you do that in Excel is you select a block of cells with the parameter named to the left of the cell where you want the number. And then what you do is how do I get rid of this thing? Oh God, I have to lower, I have to do it this way because it's blocking my thing. I go to the formulas tab in Excel and I say create from selection, and it'll automatically assume I want to do it in the left column, and I do it that way. So now if I click on a cell like E1 here, Excel tells me up here which cell I'm looking at. If I click on the cell that I just named, B1, Excel says, oh yeah, I know that cell. It has a name called BR. And I can refer to, in my calculations equations, to BR instead of always having to refer to cell B1. This makes it much, much easier to build models when you name parameters this way. So I'm going to put a value in there of 0.4. This is just for a population model. And for the MR, the next cell, I'm going to put in 0.2 for the death rate. All right, now I'm going to go over here to the F column, and I'm going to create a column called time. And for just a simple demonstration, I'm going to build a discrete time population model. And the way I do that is to use a little trick where you grab the corner of a cell after putting in two numbers and then drag it down for 19 time steps. And this is called an autofill operation in Excel. You put in two numbers, grab the corner of the cell and just click, and it will fill down as far and drag down, and it will fill up that column with the progression that you started in the first two cells. Now in the next cell, the next column, I'm going to call numbers, NT, in the population. And I'm going to have to put in some initial number. That's a parameter, but I need to put it there. Okay. And I'm just going to set it to 0.2, like 0.2000 animals. Units here don't really matter to this calculation. All right, then the next column. So this is my state now in this G column. I'm going to predict births. And in the next column, I'm going to predict deaths. So for time 1, I'm going to predict births to be equal to the numbers in 2, the numbers for time 1, times the birth rate. Okay? So this is now a functional relationship expressed as an equation in Excel. Can everybody see this? Where my pointer is this screen big enough to be clear? Okay,
It's very clear.
great. Okay. So, point 2, that's very few births. Let me do this with a population size of 1 to start with. Then that'll be 0.4 births. And deaths, I'm going to predict as population size. I can get that by just clicking on the population size column times MR, the mortality rate. Okay. Now what I do is to predict the next times population size by applying the tautology, which is that next times population size will equal the population size the year before. That's up the cell above was the year before. Then I'm going to take plus the births from the previous year minus the deaths. So this little simple accounting where I take what was there before and add new animals and subtract deaths is the tautology in this model. Fair enough? So now I'm going to go to the same thing. If you watch my mouse pointer, it changes. If I go right down to the corner of that cell, it will change to a fine crosshair. Now, if I double click that, it will autofill the equation downward in time. But if I look at time 3, it will be predicting from time 2. If I look at time 5, it will be predicting from time 4's rates. So the whole basic setup of a spreadsheet is set up so that you can just immediately use this thing called an autofill operation to fill an equation downward in time so that its references will always be to the time before. Automatically, you don't have to retype the population tautology every year. So now, let me copy the birth equation and death equation downward in time using the same convention. So I now select the 2 cells and I get the little crosshair go there and I double click and boom, it will autofill the birth and death equations downward in time for me. But now you see that the births and deaths are changing at each time because the base population size from which they're being predicted is changing. Okay, so now I have this in these very small number of steps, I've created a population dynamics model, basically. Now a real simple trick in Excel is you can select 2 columns like time and numbers here, and I can insert an XY chart type to show those predictions over time. Now, your intuition might have been that because I assumed a constant births per animal and deaths per animal, that this population would go up like a straight line over time, but it doesn't. It exhibits the classic idea of positive feedback or exponential population growth. Fair enough? Now, it turns out that for this model structure, for this assumption about the functional relationships, the model can only predict exponential growth, decay, or no change. So if I set the death rate to 0.4, the model will predict a flat population size over time. Oh, I need to scale this graph so it starts at 0 here. So it predicts that numbers won't change. Now let me ask you a question. What do you think this model will predict about the population changing over time if I increase the death rate a little bit, like the mortality rate? If I put on a very low fishing mortality rate, for example, should the population go down to a lower level and stabilize? Or how should it behave? Now, right away, as soon as I ask you that question, most people's intuition will fail. They'll say if you only increase the mortality rate a little bit, the population should go down a little bit and then it should stabilize at a lower level with that higher death rate. Well, let me do that and let's see what happens. 0.45. Look at that. Instead of stabilizing, that population changes from exponential growth or no growth into what's called exponential decay. And if I were to extend this prediction further in time, that model predicts that the population would go extinct. It doesn't predict it would go to a lower level and stabilize. It predicts that it will never stop declining, even though I've only made a slight change in the to make the initial mortality rate be just a little bit bigger than the birth rate. Fair enough? So simple functional relationships that involve what we call constant per capita birth and death rates in population models can only predict exponential increase or exponential decay. They never predict a stable population size unless you happen to set the parameter values to exactly balance each other. Now let's go back to the exponential growth case, or where this population is growing rapidly. And let's set the birth rate up a little bit higher, like 0.6, so this thing will really grow. So we've gone all the way up, it looks the same shape, but we've now gone all the way up to 450 animals over that 20-year time period. Now let me put a different birth model in, where I assume that the birth contribution to the population follows a Beverton Hold recruitment relationship. That is, there's foraging arena structure that causes recruitment rate to the population to be limited as population size goes up due to interactions that I'm not trying to model explicitly between the juveniles and each other. To do that, I need to add a parameter. I need to add a maximum recruitment rate. I'll call it R max. And I'll name it. Actually, a simple way to name it when you're just adding one thing is to go up into here and type in R max. And it will put the name in. And I'm going to say R max is only going to be 10. So the total number of recruits won't exceed 10. So I'll call that max recruits so I can remember it. And over here, I will change the birth equation from G2 times the birth rate, and I will divide this by parenthesis 1 plus birth rate times G2 divided by R max. Okay, this is the shape of prediction for recruitment that's called the Beverton Hold recruitment model. Okay, so you have essentially what it's saying is that the effective birth rate declines hyperbolically as the number of eggs or initial births increases. Now, if I copy that new birth rate hypothesis or functional relationship downward, now all of a sudden our population, instead of just continuing to grow, starts to exhibit a basic pattern you should know from your basic ecology is called logistic population growth. Fair enough. And if I extend it forward over time, it will predict achievement of an upper level. Now, if in this model, if I go in and I increase the death rate to like 0.3 or even 0.4, the population doesn't, maybe make it even 0.5. As long as I don't make it higher than the death rate, I predict that that population will grow. It just will reach a lower asymptotic or maximum size. Okay. Now what I have basically done here in general systems terms is I've incorporated negative feedback, or what we call density dependence, into one of the rate processes, the birth rate process. Fair enough. And it turns out that a necessary condition for any natural population to be able to withstand and persist in the face of changes in mortality rates, like due to fishing, is that one or the other of the rates, birth or death rates, has to exhibit increase as population size goes down, increase in relative rate. That's called compensation. So compensatory rates are a necessary condition for sustainability of populations in the face of fisheries and other disturbances. A lot of people don't realize this, that basic what we call density dependence in mortality rates in population dynamics, like the Beverton Hold recruitment model is a model for density dependent mortality of very small juvenile fish, is an absolute fundamental part of sustainability, of ecological sustainability. Fair enough? So there you've learned a couple of ecology lessons that I would bet some of you didn't learn from the bonehead way that population ecology is taught in ecology courses and textbooks. Alrighty, now what I'm going to do is I'm going to change over and start to show you continuous time models so that I can start to show you what happens if we start with something like exponential growth. So we say maximum recruits are so high that the population never effectively has a limit. So we have exponential growth. And I'm going to ask about things that can stop that growth other than the obvious thing of density dependence. And in particular, one of the oldest ideas in ecology was that one thing that can stop Malthusian growth, the exponential growth, is to have predator populations or diseases build up to stop the growth process. So I'm going to do that by building predator-prey models with you of increasing complexity. To solve predator-prey models, we almost always have to use something like differential equations rather than difference equations here, because of difficulties in predicting the predation component of deaths over time, over discrete time steps, because predation rates can change very rapidly over time. So I'm going to show you how to do the set up a differential equation model in Excel. So I'm going to set a time step increment dt for making predictions. And I'm going to make that small, like 0.1 years. I want to call it time step. Now time here, I'm going to start out with time 0 to start with. And then for the next time, I'm going to make the next time be equal to the time before plus the time step. Oops, I forgot to name this. Okay. Now I'm going to drag this down to predict for longer times. But what I'm going to do is I'm going to drag it way down on the spreadsheet. I'm going to go down to row 1000 down here. This takes me, just a few seconds to drag that formula all the way down here. About 1,000 steps. That will get me to 99.9 years of predictions at steps of 1/10 of a year. Okay, now I'm still going to have an NT column here, but I'm going to insert a column in the spreadsheet for rate of change of numbers over time. Okay, fair enough. And I'll put now my rule for change in there rather than in the formula for numbers. So rate of change of numbers in a continuous population model is equal to births minus deaths. Okay. So the difference between births and deaths gives me a population growth rate starting with one animal of 0.4. Now I'm going to copy this down so that for every birth and death number, I have a prediction of the rate of population change. But now what I'm going to do in predicting numbers change, I'm going to, for the first time step, I'm going to use an Euler prediction step. That is, I'll make the numbers at time 0.1 here equal to the numbers at time 0 plus the rate of change at time 0 times the time step dt. So it says, okay, if you just went 1/10 of a year applying this rate of change of 0.4, you'd only grow by 0.04, 10% over that. If you go by 0.4 over a year, it'd be 0.04 over 1/10 of a year. Then for every time step after that, I'm going to use the Adams-Bathford formula, and you can look this up afterward and put it up from the, you can look it up from the PowerPoint and put it in your own models. The Adams-Bathford step says make your prediction equal to the numbers at the previous time plus this weird equation dt times 3 times the derivative of time before minus the derivative the time before that, and divide that by 2. Now this is a weird formula. It was a really neat discovery about, I think actually almost 200 years ago, about how to numerically step differential equations. And what it's basically doing is it's looking not just at how fast things were changing at the time step before, but also how fast the things were changing the time step before that. So what it's basically doing here is accounting for curvature in the population growth curve over time. And accounting for that curvature gives us a better estimate of what things will be like. Okay. Now I'm going to copy that Adams-Bathford formula down over all time steps. So now I'm still making incremental. Oh, and something I always do here is I go up here on the main tab and I click on yellow here. This warns me, when I do this, it warns me that I'm using a different formula in these time steps than I did in the first time step. So the first time step was just the Euler formula, and the successive time steps are the more complicated formula. Okay? Just programming trick here. Now, just like I showed you before, if we want to plot all of those 1,000 steps, 1/10 year, we just select these two columns and insert an XY plot type. And I'll do this as a smooth one. Oh. Why is that plot not? Oh, okay. I'm only plotting the first couple of time steps here. Because it didn't autofill all the way. What it did was just to autofill down the first little bit here. And then because I had a formula in there before, it didn't autofill the rest of the way. Oh, I need to autofill all the way down to my 1,000 steps. Now we got it. And look at that. What I get now is a beautiful logistic population growth model, but it gets up to an absolutely enormous population size because I'm still using the Beverton Hold model to limit recruitment, but I've set the limiting recruitment to be just a huge population number, 100,000 recruits per year. So the population size gets up to 350 million or 350,000 before it stops growing. Oh, fair enough. Maybe something would eventually limit it. But suppose you have data that tell you that your population never gets anywhere near that size, that it maybe starts out at one animal but never gets more than maybe 50 or 100 in maximum size. Let's now put predators into this model. To make this even worse, I'm going to make this R max much bigger. So that over the 100 years, over most of the 100 years, all I will see is an exponential growth. Okay, so now we have a population growth that's growing exponentially, now to huge numbers, 10 to the 11th over 100 years. If this seems unreasonable to you, you should see what models look like for how the COVID virus grows in numbers in your body over time after you get attacked by COVID, where time is in hours, something like this. It actually is about this many hours, about 3 days before the COVID virus population in your body gets up to somewhere around 10 to the 11th. Right? So this kind of thing can happen in nature. Okay, but what I'm going to do here now, instead of...
Could you vaccinate your model, please, Coll?
When I what?
Can you please vaccinate your model? This is too scary.
Vaccinate? What are you talking about?
Vaccinate your model.
Vaccinate?
You're
Yeah, we're going
scaring
to
us.
vaccinate it by putting in a predator and see how a predator would affect it. So now to do this, let's go over here to the right of where we had the population. And I'm going to put in now another variable called PT for number of predators. And I'm going to predict rate of change of predators over time. And I'm going to do that by having predator births and predator deaths. Same basic thing that we did with the other one. And I don't know, I'm going to set some initial predator population here. What do I want to do? What do I want to set for a reasonable number here for predator numbers? I'll set it to 0.03 to a low number here. Okay. Now I'm going to make the predator rate of change equal to predator birth rate minus predator death rate. Okay, it'll be 0. I'm going to use the same formula to take numbers, oops, before plus rate of change times dt to predict population growth, and nothing will happen initially. Apply that for all times, and then modify the integration equation for PT after the second step to dt over 2 times 3 times last derivative minus the derivative before, like that. So I'm using the Euler integration. And you may notice here that the predator population doesn't change because I haven't predicted any births and deaths. Now in between the rate equation, in between the state equations for and rates for the two populations, I'm going to insert a column eaten for number eaten per time. Okay, now I'm going to have to make a functional relationship involving numbers of prey and numbers of predators for predicting how many prey will be eaten per time. The simplest assumption for this is that the consumption follows what's called a mass action. Mass action involves a parameter called AR. I'm going to set this to a fairly high number here, and I'm going to name it AR. And this is called the predator rate of effective search. That's the name in ecology for this number I'm about to use. I also need to have a parameter for the predator death rate. So I'm going to have a parameter MD. I'm going to set it to 0.5. And this is going to be the predator death rate. Per time as a proportion of the population. And I want to name it up here MD for death rate. Okay, now over here in eaten per time, I'm going to put in what's called the mass action or Volterra model. I'm going to make the predict the number eaten per time to be AR times the prey numbers times the predator numbers. This is called mass action interaction. It says more prey will be eaten if there are more prey there to be eaten, or if there are more predators there to eat them, and if there are more predators there to eat them. This is the simplest possible prediction that makes any sense at all for how changes in prey and predator numbers will affect the number of prey that get eaten. Now I'm going to copy that down. Okay. And it's growing, but it isn't affecting the prey population because I now have to modify the prey rate equation to subtract off the number eaten per time. Now what you see is that this slows the population growth down a little bit, but nothing else because I haven't put any rate of change for the predator. I've predicted that if you have 0.03 predators every year and they eat something proportional to prey, they'll eat more prey, but this product will have a constant predator number. So it will be just like a constant death rate added to for the predator. So it'll slow the growth rate down, but that's all. Now, to give this thing some flesh, I'm going to assume that the predator births are basically equal to what they eat per time. Times a conversion efficiency of what they eat into births. Oh my, it says, I don't know what an AFF is. Oh, I gotta go back over here and I'm gonna have an efficiency. I'm gonna name it EFF. And I'm gonna set it to 0.5. So this is the predator conversion. Food conversion efficiency, the proportion, how many births they produce per unit of food that they eat. And predator deaths, I'm just going to set that equal to MD, the predator death rate, times the predator numbers. Simple density independent predator deaths. Now I'm going to take these two functional models where in the birth rate is in the predator is linked to prey through how much the predators eat, and death is just linked to predator numbers. And I'm going to copy those equations down, those functional relationships downward. Whoa, my gracious, look what happened to my dynamics. Instead of just an exponential growth, I now predict a cycle. If I put the predator, I can now add predator numbers to the graph just by selecting the predator column, copying the column, selecting my graph, and pasting that as a new series. Oh, and there I have predator and prey numbers over time. So what the model is saying is that for these parameter values, what should happen is that the predators should build up and clobber the prey should then collapse, and the predators should collapse because they don't have any food, and the prey should build up, the predators should collapse, and blah, 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 like that, okay? It turns out that this is the only time pattern that the Lotka-Volterra model, this is now called, can predict if there's no density dependence anywhere in the system. It just predicts persistent oscillations. Another way to show this is if I select the prey column and I select the predator column, both of them, and I insert an XY chart. Oops, where did it put it? Why is it not inserting the chart?
I think it'll be all the way to the bottom.
Somewhere else, yeah. You
No,
probably
it
have
shouldn't be.
4 of them down there now.
Oh no, there it is. This is called the predator-prey state space. This is a way of visualizing a predator-prey system where what you do on the x-axis instead of time is you put prey numbers, and on the y-axis predator numbers, and as they move to their cycle, this shows up in the state space as a kind of an oval shape or cycle in the state space. All right, now I'm going to do one more thing and then we're going to take a break and come back, and what we're going to do is complicate this model. But before I do that, what I'm going to do is to say, well, I took away all density dependence in this thing. So if I start with more prey, like 1,000, all it does is to make things change faster. I just get crazy stuff like this. Okay. If I now reduce this maximum recruitment and I make it down around 10, what do you think is going to happen to the dynamics in the state space or over time? So all I've done is to put density dependence into the bottom of the system without using any complicated predation assumptions. Okay, let's put it in and see what that causes to happen. Whoa, my gracious, the state space changes. In fact, if we look at the time plot, what we see is that the cycle is dampening over time. Now, if I now change my initial numbers to be near the kind of the middle of the cycle here for prey numbers, which are cycling around an average around 0.2 or 0.3 and something like 0.4 and predators around 0.2. If I start down near that equilibrium, say 0.2, and predators down around up around 0.2, what you'll see is that I should be able to get this to where it exhibits no cycles at all. I need to go a little lower, 0.1 for the predators and maybe 0.2 for the prey to get this to flatten out. But I can tell you that mathematically, this model always predicts that things will eventually go to equilibrium. The closer I start to the equilibrium, the quicker, you can see how the cycles are dampening down, and they'll just keep dampening and dampening. Okay, now we need to be about 0.17 in prey and 0.07 in predators. That'll be near the middle of the circle. And now we see the thing dampening down. And if you follow this, over a really long period of time, it will eventually stop cycling. It will spiral into an equilibrium here.
10:15.
Now let me warn
That's
you
an
here
acre.
that you will not have followed everything that I say. You need to use this demonstration spreadsheet and I talk and rebuild the spreadsheet yourself before you'll really understand all of the steps that I've just shown you.
Great, thank you, Coll. This was exactly what I was going to say, that I tried it before, and I tried following Coll, and I made one mistake as we got into a little bit more complicated, and I stopped. The great benefit of what we're doing today is that we're recording it. And on the website, you will find Coll's spreadsheet, so you can download it from there, and so you have it. But it's a really good idea to build it yourself. So watch the video and try to get it, because you'll get something into your head about how you do it. And doing it in Excel first is a great way of doing it. That being said, there are other ways. I like using free software called Vensim. That's for systems analysis, system dynamics. You can do the same in Mathematica, in MATLAB. Stella is very popular, so there are other ways of doing it. The main thing is to define that you get to define the equations and that you see how things behave. We won't be doing that in the course, but focus on the package where it has been done. But what Coll showed you here when you add the faulting arena is basically the same as we're doing with the dynamic models in EWE. So this is the foundation for it. And well, pointing you to alternatives for this, such as these programs, is makes things more transparent in some ways. you can see the equations there, but it doesn't take away that to actually grasp it and to understand it, the spreadsheets are a great way to start as well. There are several ways of doing this. Carl is back, so we can continue.
Okay.
Yep.
So now you see a model that has little oscillations still, but if I lower the birth rate of the prey just a little bit, like 0.5, I make them less productive. This thing will dampen a little more quickly. Oh, no, I guess it won't. I won't bother. It should dampen more quickly, but I have to readjust to the equilibrium, so I won't bother doing that. Now what I'm going to do is I'm going to introduce another parameter in this model called HT. I'm going to name it HT. And this is called the handling time. So what I'm going to do is now I'm going to put in Holling's type, what's called the type 2 functional response to limit how fast predators can feed. So this is going to cause the food consumption rate per predator to reach an upper limit where the limitation is because of the time spent processing or handling each prey that the predators eat. I'm going to set that to a fairly large value like that to really crank a limit onto the predators. And over here, the eaten equation for the numbers eaten, that's just this simple mass action. The way I incorporate Holling's disk equation is I just divide this equation by 1 plus AR times HT times the number of prey, G2. So what this does is it essentially reduces the search rate of the predator whenever prey abundance is high. What it's modeling is when prey abundance is high, predators spend more time handling prey. I don't even need to put the AR in here. I can just make this handling time. Okay. As prey density goes up, the predator search rate will drop because of this handling time effect. Okay. And I'm going to copy that down. Now, again, this was the first complication we put into ecosystem models in the late 1960s in order to make them more realistic. We put in Holling's theory of predation for how fast predators consume prey and the limits on that associated with predator behavior. Whoa, thing went nuts. Oh, I got a little bit too much, and my numerical solution went unstable. Okay, but what you see happening as soon as I put in that that limitation on how much predators can eat is that the system that I had predicted would dampen towards an equilibrium, I now predict will go into an oscillatory mode. It will go out, start oscillating, and the oscillations will get bigger. It turns out that mathematically, these oscillations still reach a limit, and the model behavior becomes a thing called a limit cycle. The predator-prey oscillation doesn't keep getting more violent and violent forever. There's a limit on how violent it can get that's set by the maximum oscillation. It'll still predict oscillations. What the hell? but they'll be a lot less violent. And the system will eventually reach what's the stable limit cycle in this state space. If I run it long, let me see if I can run it for a longer time by changing my time step to 0.2 years and see if I can get away with it. So I can see twice as many oscillations in time here. So this was the kind of behavior anyway that we saw in our ecosystem models. Instead of going to a nice rough equilibrium and balance like we thought a lot of these systems were naturally exhibiting, we were seeing these oscillatory behaviors for almost any parameter values that seemed reasonable to us. They slow the predators down even more, doesn't fix the problem. You still get oscillations. Make them slow them down even faster. Ooh, I guess if I get really too much handling time, then the predators just die out. So I don't want to do that. Okay. But notice here that what we're doing is not pretending that we have a correct model. What we're doing is saying, what if we change our functional assumptions? Like, what if I make the birth rate density dependent with a Beverton Hold? What if I put in Holling's type 2 response? What if? What is it doing to the qualitative behavior of the dynamic model? Okay. Now I want to make one last complication here. I'm going to insert, what I'm going to do is to put foraging arena theory into the model. And I'm going to do this by inserting a column here. And I'm going to call it VT. And VT is going to be the vulnerable number of prey at any time. Now, I told you that the basic, last week, that the basic foraging arena equation makes a specific prediction about how VT is related to abundance of the prey and predators. And to do that, I need two new parameters, V1 and V2. V1 is the rate at which, going to be the rate at which prey move into the vulnerable state, V, and V2, so this is movement to vulnerable state. And then movement back, movement to safety, back into the invulnerable state. And I'm going to set big values for these so that the prey are moving back and forth really, really fast, so that the vulnerability shouldn't affect the predictions much. The foraging arena equation for vulnerable numbers says that vulnerable numbers should be equal to V1 times prey numbers divided by V1 plus V2 plus the base predation rate AP times the predator numbers, M2. Okay, I'm just telling you that if you go back and look at my PowerPoint presentation from last week and look at how the foraging arena equation is derived from animals moving back and forth between vulnerable and invulnerable states, you'll see that it predicts the vulnerable prey density to be this inverse hyperbolic function of competitor density. Competitors in this case now being predators, M2. Oh, did I forget to name something?
Well, is APAR?
Oh, yeah, right, AR. Oh, thank you. Somebody's quicker than the old man this morning. The old man's having a senior moment. So this is predicting vulnerable numbers. Now what I'm going to do here in predicting the number eaten per time, instead of predicting from total prey abundance, I'm going to predict it from the vulnerable numbers. because it's these vulnerable numbers that the predators are actually seeing. The predators are not seeing the total numbers of prey in the G column. They're seeing the vulnerable numbers predicted from the vulnerability exchange process. They still have a limit on how fast they can feed, but now the prey availability, the prey numbers they're seeing are just these vulnerable prey numbers. Now I'll extend that prediction over time. Oh, my goodness me. Look at that. All of a sudden, the model that was predicting instability and growing instability is now predicting dampening towards an equilibrium. Shows up in the state space as instead of spiraling outward to ever larger cycles, we now see the state dynamics spiraling inward towards an equilibrium point that is somewhere around in 0.06, 0.5 in numbers of prey and predator. So just putting in even a relatively rapid exchange rate of prey back and forth between vulnerable and invulnerable states, I've generated enough of a limitation on prey availability to stabilize that ecology. And if I reduce these movement rates to like 5 and 5, the system will dampen even more rapidly towards equilibrium. Fair enough? So this was the basic discovery that allowed us to build models that exhibit stable dynamics rather than just violent oscillations. Was this idea that even weak movement, behavioral changes in prey to move back and forth between vulnerable and invulnerable states has a profound effect on the basic stability properties of predator-prey interactions components in ecosystems. Put it back to 100 here. Okay. So there's basically all the things that I wanted to demonstrate to you this morning. The main lessons here are that limiting predation rates by recognizing the limits that predators have on how fast they can search for food and how much they can digest has a fundamentally destabilizing effect on ecosystem dynamics. And that's true whether you're looking at just one predator and one prey as your ecosystem, or even more true and more violent if I were to build a bunch of columns here for multiple prey and multiple predators. And in contrast to that, prey behaviors, where they limit their spatial distributions and activities in a way that limits their access of predators to them, has a profoundly the opposite effect, a profoundly ecological stabilizing effect. Now, I'm not sure what the next thing I might show you might be.
Well, then maybe you could answer a question from me. You mentioned handling time and you mentioned hulling. I wonder if you would tell us what hulling's functional responses are, the different types, and how they relate to a foraging arena.
Yeah, well, hulling classified functional responses as being of 4 basic types. I've forgotten all of the types, but the first type was basically the one we put in initially, the mass action type that just says more prey, more predators means more consumption. No limit on the predator. The second type was the one we just put in, where we put in this denominator thing to represent predators spending less time foraging when there are more prey around, because they're spending time handling prey they've already eaten. Okay, that's called type 2. Type 3 is the sigmoid functional response, in which the predator is assumed to lose its search image for prey when prey density is low, and that creates a sigmoid functional response shape. I can put this in just by raising these K2s to a power to create a thing called the Fuji equation. I won't bother doing that for you. You can do it on your own time. And then the type 4 effect, which occurs in some systems that Buzz studied, that Halling studied, as you increase prey numbers, the total number of prey eaten actually goes down. The number eaten per predator actually goes down. And there's a number of mechanisms that can cause that. One of them is prey interfering with the predator's search behavior. So that somehow, when prey densities are high, they make themselves less vulnerable to the predator by doing things like warning each other that there's a predator around, and where it takes a lot of them to be around in order to warn each other. That gives you the thing called the type 4 functional response. Most ecosystem modeling has been done either with type 2 or type 3 functional responses. The Halling derivation, they were thinking about changes in the predator. He was thinking about changes in predator behavior when he derived the type 3, the predator forming a search image or not. It turns out that changes in prey behavior through the vulnerability exchange dynamics can cause a type 3 functional response because of changes in the effects of prey density on the search rate of the predator. You saw that in the talk last week when I showed you that very simple example of an aquarium where you put a rock in the aquarium and the prey can exhibit this vulnerability exchange process. And as soon as they do, none of them come out and get eaten unless they're so crowded that they get hungry. That generates a type 3 functional response shape, not from the behavior of the predator, but rather from the behavior of the prey.
Thank you, Coll.
But
And
it's like an Ecosim, instead of thinking about it as a property of the predator, it's much better to think about all the different ways in nature that these vulnerability exchange processes occur. All the things that Will discovered, all the implications that Will and I discovered of spatially restricted foraging activity. I should mention another Will thing at this point. Something that happens in Ecosim is, what happens if I add a variable to this system, no matter what I call it, that has really high rate constants for its births and deaths and so on? What will happen in that case is the system becomes mathematically what's called stiff. And then I will get unstable prediction calculations from using a long time step like 0.2. And there's two ways to deal with this. One of them is to just shorten the time step so that the fastest changing variable in your model determines the allowable time step. That's called dealing with the stiffness problem. The second way to do that is to do the time stepping hierarchically and to have something over here on the right in your spreadsheet or in the loop structure of your model that updates the fast variable using the same integration methods, but at much shorter time steps. so that for each 0.2 years for these slow variables, the model would go through 10 steps of 0.02 to update that variable that's changing so rapidly. That's called nested time stepping. Well, the Ecopath software has one instance where nested time stepping is used, and that's in the EcoTracer routines. And what happens in EcoTracer, it's trying to trace things like contaminants moving through ecosystems. And when you look at the equations to do that, the movements of tracers through lower trophic levels in an ecosystem are very rapid. So tracer concentrations will come to equilibrium very rapidly on timescales of days in the phytoplankton of an ecosystem, and yet take much, much longer, years, to stabilize in the predators in the system. So what Will did to deal with that is he built this nested time stepping thing into the Ecosim code so that it did some of the EcoTracer contaminant concentration calculations on a much shorter time step than the rest of the Ecosim variables. Fair enough?
Yeah, thank you, Carl. Carl, we do have a couple of questions about vulnerabilities, but I think to round off what we've been talking about here, you mentioned Buzz Holling several times. Who was Buzz Holling?
Oh, my lord. If you don't know who Buzz Holling was, yeah. Buzz
Maybe
Holling
I do.
is one of the first serious mathematical ecologists who started out working actually as an experimental ecologist working on insect systems. And he was interested in the effects of predator-prey interactions in forest insect systems and in understanding how things like the limited feeding rates of birds in a forest limit the ability of birds to limit insect forest pests. He was also interested in the basic biology of predation and in finding equations for describing such effects as the fact that predators have only a limited amount of time to spend feeding. So if each prey they feed on takes some of that time, that places a limit on how many prey they can capture. So Holling developed what we call the fundamental theory of predation in ecology. That was his first major contribution to ecology in the 1950s and 60s. He then, after coming to UBC and going to other places like the International Institute for Applied Systems Analysis in Vienna, broadened his thinking to develop the general idea of resilience and multiple equilibria in ecosystems. And more recently, the panarchy idea about designing ecosystems that are resilient to disturbance and persistence in the face of unpredictable inputs and changes. So in the minds of a lot of people, Holling is the foremost ecologist of the 20th century. He died recently.
Thank you, Carl. Bea, you had a question?
Yes, can you hear me?
Yes.
So my question is like, that is any biological limit for the vulnerability numbers, for example, like V1, V2? Because as I understand, you can model like any upper limit, but that is like something that's like biologically sound, that's like you can't surpass this value.
Yeah, well, what happens is that V1 basically sets the maximum predation rate that can ever occur. V1 times prey numbers is the maximum rate at which animals enter the vulnerable state and can be taken by predators. So if we observe in the field that no matter how abundant predators are, the prey mortality rate never goes above, say, 0.5, we can immediately use that to infer that V1 can only be about 0.5, no matter how many predators are around. So there are a few cases where we have observations of prey mortality rates at highly variable predator densities, where we can get an idea at least of this V1 rate of becoming vulnerable to predators. But these rates can be sometimes much higher, yet still cause limitations on predator consumption. And they're pretty unpredictable, actually. They depend on the details of the prey and predator behaviors. Think back to that picture I showed you last week that Will drew of all the different ways that juvenile fish have to limit predation risk, vertical movement and exchange and so on. And all the different ways that their prey see less effect of them than would happen if they were all mixed up in a reaction vat. These vulnerability exchange numbers are generated by complicated biology. So what we do in Ecosim is we try to do an empirical estimation of them by varying them when we're fitting Ecosim models to time series data. Because the Ecosim time series predictions are highly sensitive to them, sometimes you can infer what those vulnerability exchanges must be just from what values you need to put in order to get the Ecosim model to predict observed patterns in a reasonable way. Low vulnerability exchange rates limit the maximum consumption of prey by a predator, but they also mean that at low predator densities, each predator becomes more productive. Each predator sees more prey. The vulnerability equation says that vulnerable prey drop down as you increase the number of predators. So if it drops down really fast, it means conversely that when you lower predator densities, V goes up rapidly, and that makes the predators much more productive. So the vulnerability exchange, the forward exchange rate, is actually related to, in an inverse way, to the intrinsic growth rate of predator populations. So people have worked out and resilience of predator populations and density dependence in their feeding and productivity with a kind of funny way, that lower V1 values imply higher productivity per predator when predator population sizes are low. So the answer to your question, it's a good question, is that it's actually complicated to figure out what these ought to be, and we try whenever possible to infer at least limits for these vulnerability exchanges by looking at long-term time series behavior from in actual populace ecosystems. And we don't have, there cannot be a clear theoretical basis for predicting what these numbers can be. They have to be determined empirically. Okay, more questions?
Yeah, thank you. And Valerio?
Yeah. Thank you for the nice presentation, Carl. I have a question. Can you associate a change of vulnerability associated to environmental variables, such as temperature or fishing pressure, for example? Because at the moment we are assuming it's constant through time.
No, Ecosim has a couple of different ways that it varies the vulnerabilities. One of them is you can directly model the fear effect. That is, you can make the rate at which the creatures become vulnerable to their predators directly dependent on predator numbers. So you can make them come out of hiding less frequently as a direct function of predator numbers in the system. So you can link them that way. We also have what are called what are they called, Billy? Oh, you can put linkages on these vulnerability exchanges to other variables in the system. They're called mediation functions in Ecosim. So you can say, I believe that the vulnerability exchange rate here depends on turbidity in the water. That prey become less vulnerable to my predator when it can't see as far. When the predator can't see as far because the water is turbid. The same thing we can do with the predator rate of effective search. We can make the predator rates of effective search vary inversely with variables like water temperature and turbidity. When we do that, what we have to do is to provide a time series of the variable that causes the effect. And then we have to provide a functional equation or a shape function for how the rate of effective search or the vulnerability parameters are affected by that mediating influence. Another example of this is this mediation is birds in marine ecosystems. Marine birds mostly feed, with a few exceptions like cormorants, but most marine birds feed near the ocean surface, right? And what we see out in the pelagic ecosystem is that the small fish that they take as prey are driven to the surface by large piscivores like tunas. Fair enough. So when the tuna aren't around, these pelagic birds can't feed because the prey aren't stupid. The small pelagics move away from the surface to get away from risk of bird predation. So they're the trophic link between bird predation, between birds and small pelagics, is mediated by the abundance of large pelagics. And in some cases, there's actually a direct effect. People have modeled the direct effect of fishing on the vertical distributions of small pelagics. Fishing also chases small pelagics away from the surface. So you can get a direct effect of the presence of fishing boats on the availability of food to pelagic birds, the availability of small pelagics to pelagic birds. That is, you can make the vulnerability of small pelagics to pelagic birds depend on the amount of fishing effort directly through a mediation function, as well as to the abundance of piscivores that drive the small pelagics up to the surface and make them available. So that we recognizing these indirect effects, they're called indirect trait mediated effects in the general ecology literature these days. Ecosim has huge flexibility to represent more complex interaction dynamics and things that limit the interaction rates. You got to know this is a huge area of research in ecology. It's called the ecology of fear, and what fear does to vulnerabilities of prey to predators and growth, mortality, performance of prey and predators, beyond just the obvious stability properties that I just showed you here. One more thing I should mention is trophic mediation effects are one of the main causes of multiple equilibria in ecosystem models.
And it's an area we know surprisingly little about from studies. Yeah.
One of the first ecosystem models that predicted multiple equilibria was one called the green water, clear water model. People had observed in freshwater lakes that when piscivores are abundant, they suppress the abundance of small planktivores. That results in an increase in zooplankton abundance, and zooplankton then keep the phytoplankton concentration low. But experimentally, if you reduce piscivore abundances in such lakes, you get increases in planktivores that the piscivores are eating. those planktivores clobber the zooplankton. So the zooplankton stop controlling the algae, and you get algae blooms, and the lake turns green. And that's called the green state or the green equilibrium. And once the lake turns green, the piscivores may not be able to reinvade if they're visual predators, because in the green water they can't see the planktivores. Their rates of effective search depend on how much they move each day. They go way down in the green water ecosystem state.
All right, just that we have two things more on the agenda. One is Spencer was going to give a brief introduction to a classic, the Rozensweig and McArthur 64 paper, and Spencer review that next. And finally, we have a question from Laban about CMSY that I think would be useful to get in as well.
You want me to, I don't want to stay around for the, I don't need to hear about Rozensweig McArthur again.
We can do that last year. So,
Okay,
Carl,
so let me,
Laban, do you want to ask a question first?
Yes, thank you. CMSY is becoming handy for data poor fisheries, but in the last lecture, the professor discouraged the use of the method for estimating parameters for fishes. I'd like to know whether there is an alternative for data poor fisheries. Thank you.
Sure there are. There are a whole bunch of much better methods for predicting surplus production and for looking at fishing impacts. There is the CMSY actually has a structural error here. If essentially it's looking at rate of biomass change as production minus fishing. The equation they write is biomass next year is biomass this year plus production minus catch. Okay? That equation is fundamentally wrong. When production is going on continuously, at least some of the catch that's made is a production that happens during the year. In the CMSY equation, there is abundance is first increased by adding production and then reduced by subtracting catch. So that's essentially the same thing as pretending that all the catch occurs at the end of the year rather than during the year. And especially in productive populations, that structural mistake in setting up the equations can have may cause some pathological prediction errors about impacts of the catch on biomass dynamics. So there are models around, for example, that integrate production rate and catch over time properly so as to account for the fact that both the catch and the production are going on at the same time using differential equation solvers like this. There are also methods for fitting time series that treat production as seasonally occurring after catch, where the fisheries are occurring. Lots of fisheries are very seasonal. So a better logistic model in such cases, even if you want to use a logistic equation, which is dubious, is to say, I'm going to take the population this year. At the start of this year, I'm going to reduce it by taking out the catch. And then I'm going to calculate the surplus production to get the next year's biomass only from the biomass that survives the harvest. And that results in a lower prediction of production generally than if you assume that all the fish present at the start of the year contributed to production during the year. So you see the basic way the CMSY thing was formulated that did not include the kind of careful thought that I told you to do in my presentation about how whether or not the component rate processes interact with one another. In a discrete time model, think of it just this way, that deaths, like catches, over the course of a discrete time like a year, depend on how many births there were, as well as how many animals were there at the start. You with me? So, you know, you can find a bunch of software around and so on that is better for dealing with dynamic removal processes under various assumptions about the shape of the production function.
Okay. Thank you very much, Carl. And
So Coll
can
will,
I? Yes. Thank you.
so I can go now?
You are probably dismissed hereby. Thanks a
Thank you
lot.
very much.
Our pleasure. And I think we can round off the session then by Spencer talking a little bit about the Rozensweig McArthur paper.
Yep.
Yeah, and you can share your screen if you want to. Up to you.
Okay. Perfect. Okay, let's start my presentation. So I'll try and keep this kind of short, but yeah. So the paper is the graphical representation and stability conditions of predator-prey interactions from Rozensweig and McArthur, 1964. So the paper is a really early classic paper on the predator-prey community composition stability. And the questions they ask are why and how do predator-prey populations stabilize? Does the predator-prey interaction contribute to the observed stability in natural communities, or is it unstable? And in what direction does the force of natural selection drive the predator and its prey? And the methods that they used to answer these questions were several simplified thought experiments, which are very interesting and actually quite hard to wrap my head around at some points. They had some assumptions to kind of get this thought experiment off the ground. You know, assume obviously that prey population is more than zero, so that it's at a reproducible level, so that it can actually sustain itself, but also less than infinity, because we have to assume that there are natural limits to maximum biomass. We also assume the predator biomass is maintained by the prey, and that predation is more than one-to-one, of course, because of trophic inefficiencies. The predator would have to eat more prey than itself to sustain itself. And then if we do infinite experiments with different predator and prey compositions, what do we get? So there were quite a few thought experiments within this presentation or within the paper, and I'm only going to focus on one, and that was just with two species. So on the, let's see if I can get my mouse working here. Let's get a nice, where's my clicker, my pointer? Oh, never mind. So we have the predator on the y-axis and the prey on the x-axis. For a given predator, so yeah, so the prey isocline, which is the level at which prey will stabilize, is this line, A, and the predator isoline is B. And what happens is at any given amount of predator, there would be a given amount of prey that would meet this isocline. So if prey, for instance, starts at this line, if predation starts at this line, then the number of prey could be either at PI or QI. And through natural selection, let's say the prey starts here, the prey would naturally want to maximize its number of resources to the point where it hits the max available resources. But at the same time, the predators are also, with their natural selection, moving towards better predation and thus increasing the predation. So and it moves in this curve-like feature. And so if we go from PI to QI, which, at this predation level, it will, reproduction interference from the predator becomes less important as we move towards maximum resources. And at this point, it's actually the number of resources that is really limiting. So what actually happens is there's this oscillation between reproductive abilities and maximum resources for the prey, and then the predation efficiency. So it kind of moves oscillating back and forth, and that's why you see this arrow-like feature here, where it's like an oscillation that's moving towards this point. But the equilibrium and the stability is really that it's like Carl was showing this in his figures earlier. It never actually hits equilibrium and stays there. It's constantly moving back and forth. And kind of just to wrap up the takeaway, an unstable predator and prey composition will oscillate towards equilibrium because of the interactions that are regulated by reproductive rates, predation rates, resource limitations, and natural selection. And again, this was just a thought experiment. So it's important to remember that the slope and the shape of the iso lines differ between every predator and prey relationships. So you can have a much more intense slope where the changes are much more quicker for different types of relationships, or it could be a much smoother, slower rate of decline or increase. And that would actually lead to a more stable situation. So it does depend, but ultimately it will move towards equilibrium and oscillate from there. And that's what I have. And there's a lot. There's also a 3 species example within the paper that talks about plant, herbivore, and carnivores. If you want to read through that. And that's my presentation.
Okay, thank you very much, Spencer. And it's time for us to round off here. I thank you all for participating, and I hope to see you again on Thursday for the talk about Menhaden by Dave Jakaris. And that will also include demonstration, a pretty advanced demonstration of how to fit ecosystem models to time series data. We haven't worked with that yet, so take it just as a demo of how far we can take it and the kind of things that are being used in actual implementation in management. So thank you very much all, and that's it for now. Bye-bye.